So for chapter 6, we need to find the specific work and heat transfer in each of the ideal components and the cycle efficiency of a power plant that operates a Rankine cycle that has a saturated vapor of 3.0 megapascals, leaving the boiler and the turbine exhausts to the condenser operates at 10 kilopascals. So we need to find the specific work, heat transfer, and the cycle efficiency. First is we need to find the specific work. From the process 1 to 2, which is the isentropic compression in a pump, we have given the work pump is equal to the enthalpy 2 minus enthalpy 1. Substitute, we have the integration of the velocity. We have the volume dP. So it is equal to the volume 1 over the change in pressure. So we have the volume is 0.00101 meter cube per kilogram times that the given 3 megapascals, now 3000 kilopascals to convert, minus 10 kilopascals, we have the specific work of pump is equal to 3.02 kilojoules per kilogram. So before we jump into the process 2-3, we need to find the enthalpy 2. First is, we have this equation, WP is equal to H2 minus H1, which is our H1 is equal to 191.81 kilojoules per kilogram, which is seen in the property table. So our WP is 3.02 kilojoules per kilo excuse me, 3.02 kilojoules per kilogram, and our H2, which we need to find, minus our H1 is 191.81 kilojoules per kilogram, and our H2 is 194.83 kilojoules per kilogram. So for process 2-3, which is the constant pressure heat addition in a boiler. So in this process, we just need to find the heat transfer in the boiler. So we have an equation, enthalpy 3 minus enthalpy 2. So in our property table, we have given 804.14 kilojoules per kilogram minus our H2, which is 194.83 kilojoules per kilogram. So our heat transfer in the boiler is equal to 2609.3 kilojoules per kilogram. For the next process, we have the isentropic expansion in a turbine. First is our equation is the work in turbine is equal to turbine is equal to H3 minus H4 rather. So for H4, we have given 191.81 kilojoules per kilogram plus 0.7384 times 2392.82, and our H4 is 1958.67 kilojoules. So to insert, we also need to find our X, and our equation for that is S3 is equal to SF plus X times difference of SFG. So we have 6.1869 is equal to 0.6492 plus X4 times SFG, which is 7.4996. And we have an X4 of 0.7384. So we have all the value. We can now solve the heat of turbine. So we have H3, which is 2804.14 kilojoules per kilogram, minus our H4, which is 1958.67 kilojoules per kilogram. And our heat work in turbine is equal to 845.5 kilojoules per kilogram. And for the last process, which is the 4.1, which is the constant pressure heat extraction in a condenser. For that, we have an equation, enthalpy 4 minus enthalpy 1. So our in enthalpy 4, we have 1958.67 minus 191.81 kilojoules per kilogram, and our heat transfer in condenser is equal to 1,766.9 kilojoules per kilogram.